first in their oh sorry then they knew the weather, climatic conditions, and structure. They, having structures with metal and masonry, they're pretty known of that time, so they're very good. The projects, they only had one or two lifetime projects that they worked on, because obviously it took decades and decades to build these buildings, and obviously their deadlines are a little bit different than you guys have now, where their deadlines were decades. Then we look at the modern architect, highly educated, known for their artistry. Now there's unlimited materials, and you guys probably see this through manufacturers. There's different materials that come out every year, different types of products and different data sheets. So we have unlimited materials to use now, whether it's masonry, wood, metal, glass, which is the same as the historic architect. But now we're dealing with like insulations, membranes, sheathings, finishes, and put it all on that. You're dealing with manufacturers that obviously get bonused on selling products as well. So you're not always getting the right information. So there's a big difference between materials used now and back then. What has changed, instead of having, a main chief builder and their little, assistant, there is a more integrated design team. There's more specialists involved, and more junior architects are actually getting involved in these projects, which is a good thing. And I think it's better for the industry now that even the junior architects or whatnot are getting their hands dirty, per se, and working on these projects. It's always good. So when they get elevated to other positions, they're well versed in their craft as well. They're very good design and function. But again, the understanding of materials is a little bit different compared to the historic designers, because again, there's so many materials, you can't keep up. Manufacturers coming out with materials every year, and it's hard to keep up, especially in your specifications and whatnot. So focusing on the good design and function is key. Again, you guys are also working on multiple projects yearly, not over your whole career. So you guys are swamped with work. And again, deadlines, you can even see days, weeks, and months. So your deadlines are a lot quicker and needed right away. So it actually puts a lot of pressure on you. So it was just an introduction, what I typically give to the builders and contractors, to show that, hey, you guys are under a lot of pressure, and it's a lot different than what you think of probably a modern or a historic architect would actually be. So take it for what it's worth. I just usually talk about that. But getting into the meat and potatoes, I guess you could say, of the building science aspects. So what we're going to cover again is the control layers. When we talk about control layers, it's what is actually required in the building enclosure to make sure you're designing a resilient and durable enclosure. So we're going to talk about that. Again, the second law of thermodynamics, which is probably the most important fundamentals you need to know for designing wall enclosures. We'll talk about the dew point, which is the biggest issue we have in our buildings, why condensation occurs in our walls. And also wall configurations for cold climates. What's the best way to design a wall enclosure to make sure it's durable, sustainable, and the most efficient building? And lastly, thermal bridging, which has becoming more, I guess, popular now that it's being introduced into the building codes. How do we deal with thermal bridging and whatnot? So when we get started, this was an article or a document that was put out by PA, and basically what we should be doing is building for failure rather than building for success. Is this document here? It's called the Moisture Control Guidance for Building Design, Construction, and Maintenance, and it talked about a study that the EPA did where they selected, you can see here, about 100 random public and private buildings across 10 US climatic regions. And basically what they found is that 85% of those buildings were damaged by water at some point in their life, and 45% is actually were leaking, I believe, at the time that the data was collected. So we know our buildings are going to leak. As your building's not going to leak. It is going to leak. So we have to design what will happen when water gets in our building enclosures. You know, it's nice when you guys do your details, it's all straight. But when you get to the job site and, you know, let's say the contractor is having a bad day and doesn't follow your guidance directly, there could be some issues. And a lot of the issues we see, again, as this document says, is moisture. So how do we deal with moisture in our building enclosure? Okay, so when we look at the 4 control layers for resilient design, these are the 4 layers that must be required in your building enclosure for it to be successful and for it to be durable and functioning, especially in cold climates and moist climates like yourselves. So it's the water control layer is the first layer. So basically it's to shed the water away from your building, away from the exterior. And if you don't do that, obviously the big issues is durability in your building enclosure, and it's going to be a lot of repair cost to your clients. The second one, air control. This is to minimize the air infiltrating and exfiltrating out of your building enclosure. And if you don't take care of this, is condensation because with that air is going to come moisture and indoor air quality, which, you know, occupants nowadays are requesting higher levels of IAQ in their buildings. So mold and whatnot is not a good filler for your buildings. So indoor air quality is becoming more and more popular with occupants for obvious reasons. Third one is the vapor control layer. So when we talk about vapor control layers, people always think that we have to stop the vapor from getting where it wants to go, which we're going to cover in a few slides. But sometimes it's okay to allow the vapor to get out. And in the case of if your wall is leaking and you have, say, 2 vapor retarders on each side, that vapor can't get out. So there is going to be, again, condensation, and you're going to have resiliency issues in your building. So you're going to have to design your vapor control layer to be the right vapor control layer and just not to stop it. Okay. And the last one is the thermal control layer, which is obviously to reduce the transfer of heat, stop burning fossil fuels for obvious reasons, energy costs to the owner. And again, it does have some condensation aspects to do with it. So again, when you guys do your drawings, you're always going to have to look for the water control, air control, vapor control, and thermal control. And sometimes it's good to even mark that on your drawings so the contractor or the builder knows, why are you putting this layer there? Oh, this layer here is because it's vapor control. This layer here is actually controlling the air. So it's good to divvy it up. And I tell my students, sometimes do them in different colors so people know what they actually are. So this is important. Remember, when you do your drawings, you have to have these 4 layers in place for resilient design. Okay. And it comes into play here is when you have these types of insulations. You can see on the top here, you have fiberglass, mineral wool, XPS, EPS, open cell foam, closed cell foam, and a 1-pound open cell foam. So these are probably the traditional insulation types that you would probably see on a job site. And on your left-hand side, it's going to tell you, is it a thermal control? Is it a water control? Air control, and vapor control. We won't go through all of it, but this is a good chart. I'll give this to Nicole so you guys can have it in the future to reference. But it just helps you, what materials can I use and where does it apply in the control layers, okay? So this here is the second law of thermodynamics, and it sounds difficult, but it's fairly easy to understand. And once you understand this, again, you could look at a wall enclosure and say, hey, is this wall enclosure going to work a climate zone for you guys? And obviously it's a wet and cold climate, same as here in Canada. We're a little bit more dry, but you guys are on the East Coast. So moisture is a big issue for you guys as well. But basically all it's saying is that the second law of thermodynamics states that the heat energy cannot transfer from a body of lower temperature to a body of higher temperature without addition of energy. Don't worry what that says. Basically, all it says is that whether you're talking about temperature, relative humidity, or air pressure, they all want to be equal. So this being said, what the second law of thermodynamics says, if you have a temperature in a room, say 76 Fahrenheit, and the outside is 32 Fahrenheit, heat wants to go from high to low to equalize. So it's going to go from inside your building to outside your building. And if it was reversed in say the summertime, say you have 90 degrees outside and 76 on the inside, that means the heat wants to go from outside to inside your building. When we look at relative humidity, which again is the big factor for condensation in our buildings, it's the same thing. It's saying that if you have high humidity in your building, it wants to equalize with the relative humidity on the outside. So in our buildings, say in the wintertime, they're hovering around, say, 40 to 50 degrees RH, or RH, or percentage RH, sorry. And then outside is about 30% RH. So the RH wants to go from inside your building to outside your building to equalize. And the same thing with air pressure. When we have, all our buildings now are pretty much pressurized. So all that pressure of air is forcing itself to get to the outside and want to equalize with the outside. And why does this matter is when you ever have transfer, you know, say from hot to cold, from more to less, and from high to low pressures, with that is pretty much going to come moisture. And that moisture wants to move with the air, with the temperature, and with the RH. Okay, so this is a big, I guess you call fundamental that you must understand for good enclosure design, that everything wants to be equal. Everything has to go from high to low, more to less, and from hot to cold. Okay. And just to bring this into practice, you know, on the left-hand side, I'm sure you guys all were at your partner's house and say their parents cooked a nice goulash meal or something like that, and they give you these containers to take home. And basically, it's the same thing as our building enclosures. If you take moist, warm ingredients, say the ingredients are us living in these buildings, and you put them in an enclosure, and then you put this enclosure, say, in the fridge, obviously you open up the fridge the next day and you see all this condensation occurring in these containers. And it's the exact same thing that happens in our buildings, is that we're inside, it's hot, it's humid, and the vapor wants to go from hot to cold, but it can't get out because we use plastic. And in this case, this plastic is a vapor retarder. So we get condensation occurring in our enclosures. So it matters where we put this vapor retarder, because if you put it on the wrong side, you could have all this condensation occurring in your building enclosure. Okay. The next one, we've all seen this. When you look out the window in the wintertime before you have a shower, usually you could see out without any issues. But then you take a shower and then you come out and your window is completely fogged up. Hopefully you have your blinds down at that point. But what happens there is the temperature in the room is staying the same. In this case, let's say 76 degrees Fahrenheit. The only thing that is really changing is the relative humidity. So when the relative humidity increases, now that relative humidity is trying to get from high to low. It's moving to the outside, and it can't get out because that glass is actually a vapor retarder, and then it condenses from a gas to a liquid, and then you start getting water in this case. And the same thing happens where we don't see it, which is in our building enclosure. So if you don't have you know, a continuous vapor retarder or whatnot, you can imagine all this moisture getting through your wall. And if it can't get through some of these building materials, it's going to hit the dew point. It's going to change from a gas to a liquid, and you're going to have moisture issues in your enclosure. Okay. And the last one, again, it's just more to represent, you know, Canada. Obviously, it's an ice rink. But what this is they just change, these are air structures, and they change the pressure in the building to be elevated. And then that's how the pressure is trying to get out, and it actually lifts up the building. So this is how our buildings are pretty much acting now, is that they're pressurized systems. But again, if you come and you poke a little hole in this enclosure, you can imagine all this vapor and air trying to escape. And the same thing happens if we don't have a complete air barrier in our system. You're going to get all that moisture, all that air, all that contaminants entering your wall enclosure, and it could lead to condensation down the road. Okay. So hopefully that makes sense for you guys. If there's any questions, feel free to ask, or we could follow up at the end. So this is something that I found when I had to buy a deep freezer, and I put it down in the basement. And we all know that basements are pretty much colder, they're damp. So what happened is when I put this freezer in and filled it up full of food, a few weeks go by, I opened up the top, and what I found is I had frost occurring, as you can see, if you can see my mouse, all in the corner of this deep freezer. So what's happening there is what you could notice, if you could see on my mouse, there's a little pinch in the seal. So you can imagine, again, this is our building enclosure here, and there's a little missing gap. You can see it's a little pinch right here. So what happens is now is that it's cold outside, or sorry, inside the freezer, and the basement is damp. So now all that moisture wants to go from high, which is the basement, and when it's cold, usually you have a higher RH, so it wants to equalize. So all that moisture was going just through that little, few millimeter pinch, and it was condensing. So you would get all this frost in this case, in your building enclosure. So it's just showing you that even minor little imperfections in your building enclosure could have if there's a high level of moisture, because moisture is the number one detriment to our buildings. So basically, the right-hand side is just showing that typically when you do wall designs, you should do calculations to determine where the dew point is actually going to happen, and is any vapor retardant material on the warm side or cold side of that could lead to condensation. And we used to do them by hand, but there is sophisticated software now, which I'll show you a few slides from now, that help designers design this to minimize the impacts on moisture. Okay, so this is the dew point. Sorry, I forgot to change this chart. It's in Celsius instead of Fahrenheit, but maybe I could, when I send it to Nicole, I'll see if I could find the imperial version and switch that out. But basically, all it's saying is, deal with me in Celsius for a second. But let's just say your room is 25, and this is going back to that shower scenario here, okay? So you have 25 degrees on the inside of your building, and say you have a relative humidity of 50%. So basically you come across and it will say at 14 degrees Celsius, you will have condensation in your building or on your exterior walls. So anytime that wall assembly hits 14 degrees, you're going to have condensation. So that's a 9-degree difference. But let's just change the relative humidity. Say again, you want to take a shower. So you're at 25 degrees Celsius. Just say, let's get up to 80. Okay, then you come to 80 and you come across, you're at 21. So now there's only a 4-degree difference that you needed on your exterior wall to occur. So again, this is just showing you that moisture is the big issue in our buildings. And if you have vapor retardants in the wrong location, you could have issues because of dew point. And I'll show a few real life scenarios moving forward. Okay, so I'll switch out this graph and I'll put in an imperial one for you guys. So how we tell architects or help, we don't tell them anything, guide them in Canada, is there's 3 ways how to design exterior wall assemblies. And the first one is all inboard insulation. So this one here has been, typically been around as long as we probably been alive, but it's not the most efficient one. So what we're starting to see now here is a split insulation system. So what that is you have some insulation inboard and some insulation outboard. Okay, so all the building codes now are moving towards prescriptive and performance pass. So you probably came across this scenario. But the best way to insulate is insulation all outboard. And again, we're not there yet. Eventually we'll get there, but there is some issues using that. We'll go through them. And but those are the three ways that we insulate in cold climates effectively. So when we look at the best one, which I just mentioned, so it's the most efficient and most effective solution. So the dew point. So we just talked about the dew point and the temperature. So if you can imagine, you have the inside of your building here, you got your interior finish, you got your cavity, empty cavity, you got your structure, and then you got your sheathing. And then in this case, we use spray foam here. And because we're using spray foam, it meets all four control layers. We don't need any membranes or whatnot because that controls the controller. But what the benefit is now your dew point is happening in the middle of the insulation. And it's only a theoretical dew point because in insulation, closed cell insulation, dew point won't occur. But what that means is when you have your dew point all outboard, so even if we look, say, at a mineral wool, where the dew point actually matters, it's outboard of your building enclosure. So if condensation occurs, who cares? Doesn't matter. It's outboard, and you would have a membrane behind it, so there's no issues with moisture. So this is the most efficient way to deal with moisture and dew point, is have your insulation all outboard. Okay, you have minimal thermal bridging. So all this insulation is protecting your thermal bridging through the wood studs in this case, and we'll talk about steel studs in a few slides from now, but it has a big impact as well. Like I said, so obviously I work for a spray foam company, but spray foam can eliminate the secondary moisture control, which would be, say your Blueskin or any type of membrane like that. Increase your interior square footage, doesn't really matter. But then what's important here is keep your service void free and open. So now you could run your services, and if anything happens, you can actually fix it quite well. So you can imagine now, if you have insulation in that cavity, say spray foam, and something goes wrong, you're gonna have to carve out all that spray foam to fix some of these services that are in there. Okay, so again, this is the best way, most efficient way to design an enclosure. But again, I don't think we're there as an industry yet. Where we are right now, again, is in this scenario, which is the second most efficient and effective solution. So the big issue, what we have here, is the dew point fluctuates between inboard and outboard. So depending on your summer and winter conditions, your dew point is going to fluctuate between these two layers. So you could eventually get some condensation occurring here, which we don't want. But what we start doing now is make sure this insulation is always permeable. So the only insulation I recommend when you do a split system is vapor permeable insulation on the outboard, whether that's rock wool insulation and vapor permeable spray foam. I don't typically recommend XPS, EPS, because again, if you have the dew point happening and condensation occurs, the moisture can't get out and it'll be trapped within your system. Okay, it's effective thermal bridging because it still protects some of the structural elements, but again, you're going to get heat bypassing the insulation, and it's going to pass through these structural elements. And I'll talk about it when we talk about steel studs, because it does have a big impact. Again, yeah, don't worry about interior square footage. That's more for building owners. Service void is eliminated. So again, once you fill this void, it's hard to see your services and whatnot, but it is what it is. Lastly, this is where we are, or where we were. We hopefully progressed from here. So now when we look at this type of system, the dew point is always happening within your building enclosure. So if condensation occurs, liquid is in your wall assembly, which obviously we don't want. You have high amounts of thermal bridging, so there's no insulation that is protecting your structural elements. Your exterior control layers need, so you'd have to look at where your control layers are, and are they the right control layers? Because some commercial buildings, as you guys know, they have vapor retarder on the inside, and then they put a Blueskin on the outside. And then again, if you get condensation occurring here, you're essentially putting a vapor barrier on the inside, a vapor barrier on the outside, which is not typically recommended. So you'd have to look and design your building enclosures and building layers effectively. And again, service void eliminated. So this is typically how we guide architects, say what wall do you actually want to design, and then we take whether it's all outboard, split system, or all inboard, and try and design a system that is always drawing in one location, whether it's drawing to the interior or drawing to the exterior. And when I say drawing, it's saying one element of your vapor retarder is actually allowing the vapor to dry. So when water gets in, you know, say around penetrations, windows or whatnot, the moisture could get out. And you need how it needs to get out is having a vapor permeable surface and whatnot. So that's why when we recommend a split system, all the insulation outboard should always be permeable. Okay. So thermal bridging, this is, you know, a joke in the building science industry. It says you need to wear your sweater and don't eat your sweater and throw it in your ribs. All it's saying is you have to protect yourself for being cold. Don't stick it in your ribs because you'll still eventually be cold. So you can laugh, don't laugh, it doesn't matter. It's just a building science joke. But anyways, this is what it looks like when we talk about thermal bridging. And so these are details that we do for architects as well, is we show them how heat is going to transfer through your building enclosure. So if you look at the top, this is an all inboard insulation scenario where you have, you can see that the top is the outside, then you got your exterior sheathing, then you got your steel studs with insulation in the cavity, and then you have a little bit of an airspace, and then on the bottom is your interior finish, say gypsum or whatnot. So what you can see, I never put in the actual temperature gradient through there, but red is obviously hot, and green, blue, and purple are cold. So basically what's happening is you have insulation between your steel studs, as you can see here. And what it's showing is that all the heat from inside your building is bypassing your insulation through your steel studs and dropping all the heat outboard of your building enclosure, which obviously is not good because it reduces your effective performance of your building enclosure, which I'll tell you the percentages in a few minutes from now. Then we want to look at a split system. So the split system here is you still get the heat bypassing the steel studs, but what we do is we put an exterior insulation to protect the steel stud. So at least it's stopping the heat flow through you know, the exterior insulation at this point. So it's still an effective solution, but not as effective as if you put all the insulation outboard. And so when you move all the insulation outboard, you can see that the temperature gradient is pretty much flat through the whole assembly, except we're going to have fasteners and whatnot, but it's pretty minimal compared to having, you know, steel studs every 16 or 24 inches on center. So this is just more of a thermal view of how to look at the inboard split system and outboard insulation. All right. So this is what I was telling you, is that when we look at wood, usually obviously residential light commercial construction, you get about an 18 to 20% reduction in your R value due to thermal bridging. Okay. But when we look at the steel stud, as we can see here, is, you know, more on the heavier side of commercial construction. If you're using 3 5/8 steel studs, you're going to lose 50% of your R value. If you go to a 6-inch steel stud, you're going to lose 70% of your R value. And if you go to 8-inch studs, you're going to lose about 80% of your R value. So this is why on the commercial side, we always try and put insulation outboard, especially when using steel studs, is because there's such a reduction in R value that 1 inch of insulation outboard is better than, you know, 8 inches of insulation in the steel cavity. So this is what we show architects and how we help them design their enclosures, so they're not using as much materials and they're doing it in a way that is sustainable and functions and is fairly resilient. So just remember the difference between wood and steel, where wood has an R value of about 1 per inch, and the R value of steel 0.00001. So it's obviously there's quite a discrepancy between the two. All right. So, so basically, how we applied some of these projects and what I talked about the the control layers and the thermal bridging into real life scenarios is that we worked on this. In this case, it was one of the largest passive house retrofits in Canada, and excuse me. And what we did is we did the perfect wall scenario, and the perfect wall scenario is pretty much insulation all outboard. Okay, that's what they call the perfect wall. If you ever read, Joe Stiebrick or John Straub's documents, and Stiebrick's actually out by you guys out in Boston area. It's a good read. And basically what they did here is you can see steel bracing here, but what they did, instead of putting it right back to the substrate, they used fiberglass clips and only used a little bit, say I think it was about 1.5 inches by 1.5 inches Z-girts fastened to here. So you would get pretty much the full effect R value of the insulation instead of it transposing it all the way back, where you're going to get, in this case, it was 6 inches. So you would have got about 70% of the R value. In this case, they're only losing about, I think it was about 20% of the R value. So there's different solutions out there. Instead of having steel bypassing all your insulation layer, there is insulation clips out there that are now available. Even though they use spray foam, which is all 4 control layers, because it was a passive house, they wanted to make sure that it was very airtight. So they also put a Blueskin behind it, and that was just more for the air tightness, which is not really needed in the building science world if you're looking at control layers. But for air tightness, passive house world, that was required. And the product that we used is, well, in Canada, come 2021, all spray foam in Canada had to have an HFO blowing agent, which means that all the blowing agents in Canada had to have a GWP of 1, which I just got an email earlier today. For the US, I think by the end of this year, all spray foams have to have an HFO blowing agent, which has a GWP of around 1. And just give you an idea, I know you guys are already there in Massachusetts, but some of the other states that you guys have, they're using blowing agents that have a GWP of 1300, which means that it's 1300 times worse than carbon dioxide. So it's a very bad chemical, I guess you could say, but at least they're phasing it out. And there's not an issue. You guys are already there, but like I said, if you're designing outside Mass, by 2024, all thermal insulations that are spray foam should have this HFO requirement. Okay, so this one here was up in northern Ontario, close to my hometown. It was a BMW dealership, and we use the split system here. And why that matters is we use the 2-pound spray foam, which again acts as all 4 control layers. We use that on the inside for thermal control and for air control and vapor control. And on the outside, we used a vapor permeable insulation. And basically why we wanted a vapor permeable insulation is because when water gets in our building enclosure, it's going to diffuse to the outside because there's a high moisture content where it leaked, and it's lower on the outside. So now that vapor drive is going to pull essentially that moisture through the permeable insulation, and it could dry. So even though we put vapor permeable spray foam on the outside, we could have replaced that with rock wool, and it would have worked as well. I wouldn't have recommended XPS or EPS in this scenario because, again, it's impermeable, which I just noticed I made a mistake. So when I send this to Nicole, I'll change it. I have permeable on both, but I have to change one to non-permeable, and the non-permeable is on the inside. And we only use 2 inches on the inside because at 2 inches, technically, spray foam is a vapor retarder. And again, it was steel studs on the inside, so we didn't want to put too much insulation on the inside because we're getting such a high reduction because of the steel studs thermal bridging. Okay. And again, HFO blowing agent. And the benefit about using spray foam in this application is we eliminated the vapor retarder on the inside, and the weather resistant barrier on the outside. So again, it becomes more sustainable when you're taking layers off the building. Okay, so this one, similar, this was again in the same city, but it was more of a, instead of a commercial, it was a residential, and it was a 7-story multi-use residential building. Again, we did the split system, but we did 5 inches of permeable insulation on the exterior, which is spray foam, but it's permeable. And what, I don't know if how well you guys could see it, but there's these metal girts, but there is metal, or there is insulation clips here. So we told them to use these insulation clips so you don't get the reduction of R value so much in the exterior cladding. So again, on the inside, they use 3.5 inches of fiberglass with poly. So you could use any type of insulation on the inside, as long as your outside is permeable. You could use any type of insulation you want, okay? So for this scenario, I don't know how well you guys could see it, but this was a 30-story multi-use residential building, and it was all a precast building, so we couldn't insulate from the outside, and this was a retrofit, okay? So we had to do insulation from the inside, but what we got the architect to do is, you could sort of see it, I can't really see it, I don't know if I can move this there. So what you could see is that we offset the steel studs 2.5 inches from the wall, and then we sprayed in between here. So essentially that's creating like a 2-inch continuous insulation, but instead of it being continuous on the outside, we did continuous on the inside by just stepping back the steel studs 2 inches. So we actually met the R value with steel studs, which it's almost impossible to meet our values with steel studs, regardless in commercial construction. But this is how we got away with it, is that we set back the steel studs and put the insulation in between. So basically you're getting 2 inches, in your case in the US, that'd be an R14 continuous insulation, and then we would fill the balance with spray foam. So this is how we get designers to design it if they're doing retrofits from the inside and they don't have the opportunity to put continuous insulation on the outboard. So it's becoming more popular as we see it. Okay, so this I think is the last case study. I got a call one day, and it was in Buffalo, New York, and the lady was saying that it was pretty much raining inside her in her house during the wintertime. And I said, okay, well, what was the assembly? And she said, well, we use spray foam and fiberglass. I said, okay, well, it's becoming more popular as well, without a vapor retarder. But she's like, well, we only put 1 inch. And in that case, this goes to the sense that when we're talking about the moisture transfer and dew point, so because they only put 1 inch of spray foam and then put the balance of batt insulation, the vapor was bypassing through the batt insulation, hitting the spray foam, which is a vapor retarder, and condensing. And then you can see all this water condensing on the spray foam here, and it was creating water droplets inside the house. So they're called hybrid insulated systems, but what you have to do is you have to calculate the R value thickness of the spray foam, and then do the R value thickness of the batt. You have to do a calculation to see where the dew point happens, and if it happens within the foam, you're okay. But in this case, it happened outside of the foam, which is not okay. So they had to go in, remove all this batt insulation, and they had to put the right amount of spray foam in there and put in the batt to make sure it performed adequate. So when people say, you know, spray foam's a vapor retarder, it is, but depends where you put it in the location in the wall, because it could have detrimental effects to your building assembly. So this is the calculation that we do to help with architects, and this is a job that I have at Elasticam, and we offer it to architects like yourselves. So you guys could just call me up and say, hey, Rocky, I have a wall. We want to put 2 inches of say spray foam in the wall, and then we want to put the balance of any type of insulation, whether it's fiberglass, rock wool, and we do not want to put a vapor retarder in. Does it work in, say, Salem? I said, okay, well, I'll have to look at the system, and then I put it in Woofy, which is a German software that does all these dew point calculations. And basically, what I did is I did the first scenario, or the last scenario, which you just saw in Buffalo with this lady's house with only 1 inch of insulation. So when this purple line essentially goes, the purple line is the dew point, and when it goes above the temperature, you have condensation. So basically, she had condensation for, I think it was about 4 or 5 months out of the year in her enclosure. But I said, okay, well, let's do 2.5 inches of spray foam and then put say 3 inches of fiberglass. And now you can see that there is no condensation occurring in this assembly. So it is more of a scientific approach to designing walls when you could remove the vapor retarder. And this is why I'm here to help you guys. If you ever come across this scenario, I'll be happy to help you guys out. And, you know, obviously I do it pro bono, and it doesn't matter. I just want to make sure things are done correctly in the field. So this is a software. If you guys want to get it for your office, it's a free software, and it's called Woofy, and it's a pretty good software tool. And you can sort of see it right here. You just build your wall assembly as per your design. You can drop it anywhere, and basically you could run this model for an hour all the way up to 20 years, and it's going to predict how much moisture is going to be in your wall assembly. So this is, like I said, how I help out designers. And then down here is, again, it's called Therm software. Again, it's a good software if you guys want to get into it. Pretty much you could design it in CAD, upload it into this program, and it will show you the effective R value of your wall assembly, and if there's any potential condensation as well. And there's this also, if for the people that like reading books, this is a pretty good document here, ASHRAE, A Handbook of Fundamentals, and this just talks about the building science. If you go to chapters 20, I think it's 24, 25, 26, and that will pretty much show you how to design enclosure without any moisture issues as well. So that's a good document right there as well. So in conclusion, I know I've been talking pretty fast and we're getting close to 1 o'clock. What you need to know is understand your operational climate zones. When you're designing a building, say in Salem, it's going to be different than when you're designing it, say in Florida or whatnot, because the vapor retarders are going to be in different locations. So you can't take the same wall assembly and put it anywhere. You actually have to design it for that climate zone. Ensure that the control layers are always followed, and you know the 4 layers are what we talked about above. And again, I'll give you this presentation so you'll always have it. You know, I want you guys to put the 4 control layers on your fridge so you see it every day when you guys are designing your enclosures. Utilize the 3 enclosure design. Try not to do the first one. Second one, or the all-out board, is the best. Minimize thermal bridging, and understand why you're doing what you're doing. And again, why I say that is, why are we putting the membranes in this location? So when your contractor asks you, well, why are you putting this membrane here? You know why you did it. And you say, hey, because we don't want condensation, we want air leakage into our building. So hopefully that helped you guys. I know we didn't really talk too much about spray foam, but again, it doesn't matter if it's spray foam or if it's any type of insulation. As long as you follow these fundamentals, you could pretty much mix and match any type of insulation that you guys want in your assemblies. So what we're starting to see in the industry in insulation is obviously sustainability is a big aspect. Transportation, how are we getting our materials to site? Material efficiency, how much material we actually fitting on a truck, because you know if it takes 20 truckloads to get material to a job site, it's not very efficient. So it's not really what you guys are doing. It's more how we're trying to reduce our carbon footprint for the industry. Reducing the building enclosure layers. Again, the less stuff you can put on the wall, the less you're going to have on your carbon footprint. We're going to have to look at resilient materials, hurricanes and flooding, because we're starting to see a lot more hurricanes and flooding occurring, and below grade applications, especially with foundations and floors, because usually they're neglected a lot of times in our industry. All right, so I know that was pretty quick. I think we're right at 1 o'clock. right now, but I'll take any questions if there are any. Here's my email. I know there's been a bunch of emails jumping back and forth. Feel free to use me as a resource. I'm here to help out anyone. I just want to make sure our building closures are being designed right in our industry.
Thank you so much for all this information. I think it's been really helpful for us to see all the details behind what you do and how you do it. I think I know you say you were gonna send me that presentation. So if you do, if you can also add like the name of the software that you use,
Yeah, I can do that.
that would be
Yep.
awesome. Yeah.
Yep. And yeah, my email's here. So if you don't want to ask questions and plan them here, feel free email me regardless. And I think I ordered a bunch of pizza for you guys, so you might have some to take home as well. So hopefully you enjoy the pizza as well.
Okay. Thank you. Thank you so much for the time and for the pizza.
All right, guys, you have yourselves a great day.
Thank you. You too.
All right,
Bye.
take care. Bye.